All right, welcome back everybody. In this video, we'll be continuing by taking a look at section 1.2, which involves types of data. So first of all, just to review or recap a little bit, um, when we're doing statistics, we're interested in some fact about a population. We want to know how many units the typical COD student is taking. We want to know the height of all people who live in Indian Wells or something. And because it's impractical, difficult, or impossible to find out such a fact, by looking at the whole population, we look at some of them. So we might ask some students how many units you're taking. We might find some people in Indian Wells and figure out how tall are they. Because it's just hard or impossible or too expensive to examine everyone. So we have population information. We can't figure it out always, and so we're going to take some sample information. So a couple more definitions then. A parameter is a numerical measurement describing some characteristic of a population. So a parameter might be some fact about all the people who live in Indian Wells, or all of the COD students, okay? A statistic, which is what we're here for, right? Statistics. A statistic is a numerical measurement describing some characteristic of a sample. So to make sure of the difference between the two, the heights of all of the people in Indian Wells, if we figured out the average, that would be an example of a parameter, the average heights of all the people. If we went and waited for 100 people to come out of Jensen's or whatever, and figured out their heights, just 100 people in Indian Wells, and figured out the average of the heights of those 100 people, then that would be a statistic, okay? Another example, suppose that you run a little bicycle factory and every day you want to sample some of the bikes for quality control. So let's say your factory builds 60 bicycles every day. So the population might be the 60 bicycles built in the factory in a day. And out of that, we could take 4 of them and check them for defects. And so the parameter of study would be how many defects are there in all the bikes produced in a day. The statistic would be the average number of defects among the 4 bicycles that were sampled in that particular day. So a parameter is about the whole population. The statistic is about the sample. And luckily, to remember those, you can benefit from the alliteration, right? Population and parameter both start with a P, and sample and statistic both start with an S. So, okay, more words. Okay, quantitative versus categorical data. Quantitative or numerical data consists of numbers representing counts or measurements. How many people live in your household? How long is your left forearm? All of those are examples of quantitative data. Okay. Categorical or qualitative data consists of names or labels that are not numbers representing counts or measurements. Okay, so examples of categorical or qualitative data might be political party or eye color or the model of the last car you rode in. All of those are examples of categorical data. So examples, the number of chocolate chips, sorry, color change, the number of chocolate chips and 3 cookies taken from a package. So you go to the store, open up the package of cookies, you should probably pay for it, but open up the package of cookies, take out 3, count how many chocolate chips there are. Okay, because that's a count, that is going to be a quantitative piece of information. Okay, the number of minutes 5 people waited online or waited on the phone when calling customer service. So how many minutes does each person wait? We could keep a list. There's 5 people. So we have a list of 5 numbers. How many minutes did each of those 5 people wait? Okay, so that is, again, quantitative. It's a number of minutes, even including fractions. Okay, we could figure out, 3.78 minutes, right? It's a number, it's a count of things, how many minutes there were. The city you live in, Indio, Coachella, Mecca, Palm Springs, what city do you live in? Okay, that is going to be categorical. Okay, it doesn't represent a count or a measurement, it's just a name. Okay, zip code, you have to be careful about zip code because it is numbers, right? 92260 is a number, right? But the thing is that zip code doesn't represent a count, right? Neither does area code. Zip code doesn't represent a count. It's basically a stand-in for an area, right? And so that is going to, again, be categorical. Okay, people's heights, that's going to be, again, a quantitative piece of information. Okay, be careful about numbers. Like I said, they don't represent numerical data. Uh, it's more categorical. Okay. Okay, still more words. Okay, sorry, I apologize. The first chapter here has a lot of words. Okay, out of the different kinds of numerical data. Okay, out of the different kinds of numerical data, some of it is discrete and some of it's continuous. And so the descriptions from the book here, past students of mine have found them kind of confusing, but we will try. For discrete data, its data values are quantitative. Okay, both of these are quantitative. The number of values is finite or what's called countable. And the thing is that countable is not a concept that they go into in any depth in our textbook. They just say if there are infinitely many values, the collection is countable. If it is possible to count them individually, okay, that's not helpful, sorry, such as the number of tosses of a coin before getting tails. Okay, so that's kind of not really a helpful description. Continuous, you can read through that. It's, again, not super helpful. It basically says, okay, well, it's not countable. So again, not too helpful, sorry. The best way, I think, to think of these is discrete data would be things that you count. Okay, how many people are sitting at that table? That's a count. Continuous data would be things that you measure. Okay, how many inches tall is that plant? Okay, you might think, okay, well, 21, 22 inches, that sounds like counting, but remember that you're measuring, and if you're measuring, you could use arbitrary precision, right? We could say it's 23.869 inches, right? And just keep running out decimal places for however good our ruler is, right? In general, things that you count is discrete data, and things that are measured is continuous data. Why do you care? What difference does it make? The reason why we would ever care whether something is discrete data or continuous data is that some procedures or processes we do in statistics, you use one procedure for continuous data and a different procedure for discrete data. So that's why it matters, knowing which type of data it is. Count data, discrete. Measure data, continuous. By the way, the word discrete here, I don't really grade, can't really grade on spelling for this, but that is not the discrete like D-I-S-C-R-E-E-T, which is like, okay, let's be discreet about this kind of discrete, like private or secretive or something like that. This is discrete, meaning like separated into little pieces. Okay, so make sure you're using the right word. Okay, examples, the number of pairs of shoes you own. Okay, if you want to count the number of pairs of shoes you own, that's going to be, well, I own 3 pairs of shoes or 27 pairs of shoes or however much it is, that is count data. So that we'll say is discrete. Okay, how many numbers you can make with the digits 2, 3, and 4? Well, there's 2, 3, and 4, and 23, and 32, and 43, and we could list them all out, right? I didn't say how many digits we had, so there's going to be a lot of them, okay? That is going, but we could count them, right? It's not something we'd measure. We would have a list, and we'd say, okay, well, there's 907 numbers or whatever. This is going to be count data, so it's, again, discrete. Okay, how long does it take for a tub to drain? Okay, that is going to be continuous data, it's time. Time is going to be continuous data. I know we might think of it in terms of a whole number of minutes or a whole number of seconds, but if you think about it, you can always subdivide a time unit into smaller time units if you have a faster stopwatch or quicker reflexes on your stopwatch, right? In general, though, discrete data results from counting, continuous data results from measuring. Okay, we're getting there. Okay. There's different what's called levels of measurement. There's 4 of these, so we need to look at the definitions for these and then see examples. 4 levels of measurement. The nominal level of measurement is characterized by data that consists of names, labels, or categories only. Okay, this is kind of the simplest one in a way. We're just giving names. And you can think of like the first 3 letters in nominal sound like name, right? It is the same word root as things like nomenclature does. Data can't be arranged in an ordering scheme, right? Such as low to high, okay? Or it's not meaningful to do so, right? Examples of this would be things like zip code, uniform numbers if you play on a team. So teammate uniform numbers. All right. Okay, so again, the order doesn't, there's no ordering based on this, right? The zip code 92260 is before the zip code 92262, but that doesn't really mean anything, right? So there's that. Data are at the ordinal level of measurement if they can be arranged in some order. So the ORD there is tip off, ordinal and order. If they can be arranged in some order, but differences obtained by subtraction between data values, either you can't determine them or they're meaningless. Okay, an example of this would be star ratings on hotels or restaurants. Okay, you can put them in order. Okay, this is a 4-star hotel, so it's better than a 3-star hotel, which is better than a 2-star hotel. You can put them in order, but if you're looking at hotels, is the difference between a 3 and a 2-star hotel, is that the same as the difference between a 4 and a 3-star hotel? The difference of 1, is that the same difference between 4 to 3 and 3 to 2? Is the difference between a 4 and a 2 twice as much as the difference from 4 to 3? Does it make sense to ask this question? Not really, right? So we can put them in order, but it doesn't make sense really to subtract, okay, 4 minus 3 in this cases. Okay, 2 more. We have interval level of measurement. Interval level of measurement is 1 step higher. Data can be arranged in order. Differences between data values can be found and are meaningful. So subtraction makes sense. Data at this level don't have a natural zero at which none of the quantity is present. So an example, the pretty typical example of this would be temperature. And there, it makes sense to do subtraction, right? If we say it's 70 degrees in one city and 60 degrees in another, there's a 10-degree difference, and it makes sense to talk about that 10-degree difference. Subtraction makes sense as a way of comparing. But for temperatures, when we say that it's 0 degrees, that doesn't mean that there's a complete absence of any temperature. It's just a position along a scale. And as you know, if we change from like Fahrenheit to Celsius, what's 0 Fahrenheit is not 0 Celsius, and conversely, right? It's just a number on a scale. And if you wish to introduce a different scale, then the 0 will move. But it's you're not really ever going to have no temperature. It's just the temperature could be 0 degrees, but there will always be a temperature. Okay. The highest and last one is going to be a ratio level of measurement. Data can be arranged in order, differences can be found and make sense, and there is a 0. Okay. So for data at this level, difference and ratios are both meaningful. Okay, so here's a table that shows all those levels of measurement along with examples. They're kind of inclusive, right? So nominal is the most basic. It's just names, basically. Zip codes, nationalities, eye colors, political affiliation, things like that. So you could code things like that with numbers, like say brown eyes is 1 and green eyes is 2 and blue eyes is 3, right? You could code those, but it doesn't make sense to put them in any order. You could alphabetize people's eye colors, but it doesn't really help to say, okay, blue eyes come before brown eyes, okay. It doesn't make sense to have an order. It's just nominal data. Ordinal data, 1 step above, does have order, but it doesn't make any sense to do subtraction. Grades, movie reviews is kind of like hotels and restaurants. For grades, is the difference between an A and a B bigger than the difference between, or is the difference between an A and a B the same as the difference between a B and a C? Or is it still just 1 letter grade? Is the difference between A and C twice as much as the difference between an A and a B, it doesn't really make sense to ask these questions. So data can be arranged in order, but subtraction doesn't really give you anything. Interval data, there's data are meaningful, differences are meaningful, but there's no zero, right? We talked about temperatures, also SAT score. There isn't really a zero for SAT scores, but you can talk about differences in people's scores. Ratio data, most all the processes that we'll use in this class actually work with ratio data, so that's nice. There is a zero. You can compare using division or subtraction. Heights, people's heights, plant heights, lengths, distances, how far can you jump, volumes, how much soda is contained in 50 selected Coke cans, times, ages, people's salaries, all examples of ratio data. Okay. Again, don't worry, real hard about memorizing definitions. You want to kind of know what each of all this stuff is, and then be able to, determine based on examples. If I ask you, okay, let's say that we've collected 40 of your employees' salaries, which level of measurement is that? You need to be able to decide or classify things and use the wording more so than be able to actually give definitions. Okay. We're almost done. Some examples next. Okay, so these again are taken from the textbook. In here, what we're trying to do is just decide, are each of these things statistics or are they parameters? So let's try 5. In a AAA Foundation for Traffic Safety, 21% of the respondents said that they recently texted or emailed while driving. So 21% of the respondents. Those respondents, is that every driver there is? No, it's just the survey. People who are surveyed, the respondents of the survey. So that's going to be a statistic. Statistic for sample, that's the S's. Parameter is population, right? Okay, 7, a study was conducted of all 2,223 passengers aboard the Titanic when it sank. Okay, that's all the passengers, right? It's not talking about every person who's ever ridden on a ship. It just says the study was of Titanic passengers, but they looked at all the passengers. They didn't look at like 50 of the passengers. They looked at all of the passengers on the Titanic. So that sounds like population. Okay. Number 9, the mean IQ scores for subjects taking this IQ test is 100. So the mean IQ score for subjects, that there's no quantifier in there. It doesn't say some subjects or 30 people who took it. So implied there is that it's all the subjects, and so that's going to be the whole population. Okay. Last one, let's go down to 12. In a random sample of households, it was found that 47% had HD TV. So that is should be pretty clear that is a sample statistic. Okay. In the next set of questions, we want to decide whether the values are discrete or continuous. Remember, discrete would be counted data and continuous would be measured data. Let's try 13. Honda Civic crash tests. They measured the chest deceleration, and then you could read the rest of it. 39 G, where G is the force of gravity. So it's measured, right? So that sounds like it's continuous to me. Okay, 14. The Honda Civic has 4 cylinders. Okay, well, we counted how many cylinders there are. That is going to be discrete. It's counted. Okay, George Washington was 188 centimeters tall. So that's measured, right? So that's going to be continuous. You want to be careful there that you didn't report that as discrete because it sounds like a nice whole number. It's just that they rounded to the nearest centimeter, right? We could have used a better ruler and gotten more decimal places. Okay. And then last part, a couple of these. 25, what are we doing? Identify what is wrong. So in 25, it says, in a poll sponsored by the Idaho Potato Commission, 1,000 adults were asked to select their favorite vegetables, and the favorite choice was potatoes, which were selected by 26% of the respondents. So it should be pretty obvious that if the study was sponsored by the Idaho potato people, it makes sense that potatoes came out the winner. But there's that. In 26, it says, in a USA Today online poll, 728 internet users chose to respond, and 41% said that their college majors prepared them for their chosen careers very well. So this is going to be a voluntary response sample. So I think that would be the issue with it. There's people who chose to do it. And then additionally, and this is a little more subtle, it's an online poll. And so if you're doing an online poll, it says 41% said that college majors prepared them for their careers very well. So you could ask, well, if they have time to like sit and look at this USA Today poll, maybe they're at home playing on the internet instead of being at work, right? And so, or maybe they're at work playing on the computer. But in any case, that may affect the results, the fact that it is this computer poll. Okay, and then let's skip that to 28. In the years following the end of World War II, it was found that there was a strong correlation or association between the number of human births and the stork population. It therefore follows that storks cause babies. We'll talk about this later in the course, but as you know, a correlation or relationship doesn't imply a causation. So that would be the issue with this. All right, so that takes us, yeah, we got one more. I thought I was done. Sorry. 34. In an ad for the club on a device used to discourage car thefts, it was stated that the club reduces your odds of car theft by 400%. So I don't know if anybody who uses the club still. Interesting. It reduces your odds of theft by 400%. So if you think about it, is it possible for something to decrease by 400%? I think a decrease of 100% would take it down to 0. So how could something drop by more than 100%? That's not really possible. Okay, and so that turns out to be the same issue as with 35 and 36. That you can't have something that decreases by more than 100%. All right, so that finally will take us to the end of section 1.2. So you can get started on the assignment for sections 1.1 and 1.2. Let me know if you have any questions, and have a great day.